So today, or this week, I guess, we'll start talking about beams, right? Or the beam element as it relates to finite element analysis. So we start out with the beam, right? And we assume some things about our beam, like a unit displacement, and hold some of the other things to 0. Then from our matrix, right, if we have our displacement at 1 or a unit, then we know that we can determine what the equations are for these columns or that column, and those will all go to 0, right? And so we're just dealing with one part of our matrix at a time. So we'll have we can get a value for F1 and M1. And this will be our classic cantilever beam, right? So if we look at the back of our book and get the equations for deflection and rotation or slope, then these are the equations that we're going to deal with. And we can use superposition to determine what our deflections are going to be and solve for our F, for our force, and for our M, or F is going to be our deflection, and M is going to be our moment. So we'll end up with, they'll reduce down to those two equations, plug those into our matrix, and it'll look something like that, right? So we've got our first column of our stiffness matrix determined. So to do the rest of the matrix, we can follow a similar scenario and do a unit value for each of our degrees of freedom, and we'll end up with a matrix that looks something like this, right? But this is just what? Our deflection and our moment at each end of the beam. We have more than just those 2 degrees of freedom, right? So if we add to our matrix, right? Add in the moment, and then we can go full 3D, and it'll look something like that, right? Everybody's ready to solve that hand calculation, correct?
Take me out.
So what are we looking at? Let's see, first row is going to be displacement at end 1, right? Or axial displacement. Then you have your vertical displacement. Then in the z direction, then you have torsion. So your moment on the z, then you have moment on the x, moment on the y. That all takes care of one end. And then, of course,
Charles,
this half is all the other end.
you might want to take this slide and use colors to point out the A over L and the minus A over L and the U1 and the U2, etc.
Okay.
And then, the next slide or whatever could be pointing out, another,
Highlighting each one.
because they're all just superposed, right?
Yeah.
This is all just, you're just adding stuff up.
We've included all the axes of freedom for 3D for one beam element in each end of it, right? And then you just do the matrix multiplication to determine what's going on for now. Let's see. The one thing that our stiffness matrix doesn't account for is any kind of stress concentrations, right? Or changes in geometry. We're assuming homogeneous material, a constant cross-sectional area, all those standard assumptions apply. So now that we've developed our matrix, let's go solve some problems with FEA. So to convince ourselves that that stiffness matrix is appropriate and is working and doing what we believe it's doing, we'll start out with this simple beam, with this criteria. And then we're going to develop or gain confidence in what the FEA program is doing. So to start out with, we'll do a axial load on the beam. We have equations to deal with that. We can solve for a theoretical solution. And those numbers are here. So we've solved for a theoretical result, and then we can plug it into simulation mechanical, and let's see what we get. So we've constrained the far end. We put an axial load of 1,000 newtons on the other end, and when we deflect it or get the results from sim mechanical, our theoretical solution is 8 millimeters. That's for thin beam theory. That was our PL over AE. I could have gone in and edited those and taken the shear values out of the material properties, but I chose to leave them in because it gives you a slightly different result for the transverse shear, just to make sure that you're aware that it's there. It does affect it. It's rather small, less than a 1% change, but just be aware that if on the theoretical versus what FEA is doing when you're dealing with the transverse shear, there's going to be a difference in value if you include it in the FEA versus your analog calculations. So that was our axial deflection. So let's change our scenario a little bit. Go to design scenario 2. Let's do a vertical load and check our displacement and our resistance to a moment. So our theoretical solution should be displacement of 8 millimeters. This has the rotation in rads, but sim mechanical gives it in degrees. So here's our sim mechanical setup, constrained XYZ and rotationally at one end, vertical load 1,000 newtons at the other. And we get a typo on my slide because that's not correct. Should be 8 millimeters, not whatever that number is. So my apologies there, but my rotation is correct because I checked that. So sim mechanical gives it here in, oh, I got the wrong picture in the wrong words. There's the 8 millimeters. Or the 8.02. Oh, we're having fun today. Okay. Anyway, it does come out correct because I did the calculations. So even though my slide pictures are booted up, I'll correct that. So now if we go to design scenario 3 and simply put a moment on the end, this is drawn as a negative, but when I did solution, I chose on purpose to do a positive moment. So there's our setup, and our theoretical displacement and our sim mechanical displacement match, and our rotation also matches. And my slides are off again. Okay, it's always something, right? Devil's in the details. So far, everything is corresponding and working correctly. So our final scenario, we'll put the moment on there and the load. And let's see, I have my setup correct, but my slide values are, hey, I got this one right. So we got our 8.6 millimeters. Again, I have left the shear in, I didn't take it out. So we're slightly different on the displacement versus our theoretical. For our rotation, this is the correct rotation, it's just a long slide, picture anyway. So it works, I guess. Anyway, my apologies for the incorrect pictures with the results, but I mean, I did go through the theoretical calculations, I went through the sim mechanical, they match up, it's correct, you can do the same. But anyway, so that proves that our elements are behaving as we think they should, right? So now we can do, go forward with some confidence that what we're doing for our exercises are going to be correct.